This is the opening lecture that covers the Doppler effect, also known as the Doppler shift. This lecture is specific to Conceptual Physics AB. There are two types of Doppler shift. The first type of Doppler shift occurs when you have a stationary observer, but a moving source of sound. And then the second type of Doppler shift is where you have a stationary source of sound and a moving observer. Of course, you could actually have both the observer and the source moving at the same time. Therefore, the two Doppler shifts can actually be combined together. Okay, now I'm going to go ahead and demonstrate for you the first type of Doppler shift. That's when you have a stationary observer, that will be my phone, and I have a moving source of sound. That's going to be this tuning fork, which I will then strike and twirl above my head by means of this rope. Okay, let me tilt my phone, however, off to the side so I can do this demonstration safely. So bear with me. Okay, let me tilt this like so. Also going to move it down a little bit. There we go. Okay, I'm going to give this tuning fork a whack in just a moment, and when I do, it vibrates at its fundamental frequency of 480 hertz, and then I'm going to twirl it above my head. Now, while the moving fork is moving towards the observer, moving towards the phone, the wavelength of the sound waves that the fork emits are shortened a little bit. They're a little bit smaller in wavelength than they would be if the fork was stationary. So then therefore, if the wavelength is smaller, keep in mind that wavelength multiplied by frequency is equal to the speed of sound. This then means that the frequency will be higher. This then results in a higher pitched sound. And then when the fork is moving away from the observer, then the sound waves that it emits towards the observer are stretched out a little bit. The wavelength is a little bit bigger than it would be if the fork was stationary. So if the wavelength was a little bit bigger, this then means that the frequency is a little bit smaller, resulting in a lower pitched sound. Once again, this is the first physical type of Doppler shift. So let me go ahead and give this thing a whack. Like so, and then I do this. Like so. So you hear a change in the pitch associated with the sound due to this first type of Doppler shift or Doppler effect. Okay, let me tilt my phone back. Like so. Okay, let me move it upwards as well. Like so. Okay, now I cannot demonstrate the second type of Doppler shift, but let me describe it to you, and then afterwards I'll have you pause this lecture and watch a short screencast that depicts the two types of Doppler shift by using some animation. The second Doppler shift arises from the following. You have a stationary source of sound, but a moving observer. Let's say that the observer runs towards the source. If you run towards the source from Galilean relativity, you would then see the speed of sound as greater than 343 meters per second. So then therefore the frequency of the sound wave that you would hear is higher pitched for that reason. The wavelength of the sound wave, however, stays the same. And then if you run away from a source of sound, once again the wavelength of the sound wave is the same, but you would measure the speed of sound as being less than 343 meters per second. Therefore, you would hear a lower pitched sound for that reason. So there are two physical types of Doppler shift, wherein number one, the wavelength of the sound wave physically changes, and then secondly, in number two, the speed of the sound according to the observer is different than 343 meters per second. Now, I've described this here in words in this lecture. At this point, however, I want you to pause this lecture and then watch the screencast that I described that depicts both types of Doppler shift by using some simple animation. Okay, now that you've watched that screencast, let me describe to you the following equation that we use to describe Doppler shift. I'm not going to derive this equation. To do so is a little bit beyond the scope of this course, but I'm going to give you an understanding as to how the equation works. Okay, let me write down the equation itself, and then I'll define all of the terms. Okay, so we're looking at Doppler shift, also sometimes referred to as Doppler effect, and it's governed by the following expression. this expression here. As I said, I'm not going to derive this expression. We'll just explain how it works and use it for some simple examples. Okay, the terms. Okay, first of all, F. This is the frequency that's actually emitted by the source of sound. So if we're talking about my tuning fork, for example, which has a fundamental frequency of 480 hertz, that's the frequency of the sound wave that's emitted by the fork if it was stationary. So F is equal to the sound emitted by the source, the frequency of the sound emitted. By the source. Okay, F prime, however, which is what we always calculate, that is then the Doppler shifted frequency. Okay, and then contained within the parentheses, we have first V. V is the speed of sound equal to 343 meters per second. And then we have VO and VS. The VO refers to the speed of the observer. The VS refers to the speed of the source. And then we have the symbols, the plus and minus signs that you see appearing in this manner in the numerator and in the denominator. It's easy to remember which symbol means what. The top symbol always means towards. The bottom symbol always means away. So the top symbol means towards, T for top, T for towards, so it's easy to remember. And the bottom symbol means away. So for example, in the numerator of the expression, the plus sign, which is the top symbol, that refers to the observer moving towards the source. The bottom symbol in the numerator, the minus sign, that means away. That refers to what happens when the observer moves away from the source. And then in the denominator of the expression, notice that the symbols are reversed. The minus sign, which is the top symbol, top means towards. The minus sign means that the source moves towards the observer. The bottom symbol means away, the plus sign, so the bottom symbol means that the source moves away from the observer. So all that we have to do is look at the situation, get the directions correct, and that then tells us which symbol we then use in the expression. And then therefore at that point, we just plug in the values that we have to calculate the Doppler shifted frequency. So we'll take a look at a couple of different examples. Let's go ahead and start with an easy example to begin with. That will conclude this lecture, and then I'll do a couple of other examples in the lectures that follow. But for now, let's go ahead and take a look at the first of our examples. Okay, I'm going to do some erasing here. Okay, and in the first example, we have the following. We have a stationary source of sound. To make sure, of course, that you copy the problem down into your notes. We have a stationary source of sound that emits a frequency of 500 hertz. So that's the value of F, 500 hertz. Keep in mind, by the way, that the speed V, which is the speed of sound, is the 343 meters per second. Okay, and then an observer is moving in a car at a speed of 20 meters per second. So we're given that VO is 20 meters per second. That's the speed of the observer. By the way, because the source of the sound is stationary, this then means that Vs is equal to 0. Okay, and then it says, what is the frequency heard by the observer if the car moves towards the source? And then secondly, what happens if the car moves away from the source? So let's call this part A and part B of the example. Let's do part A like so. So the car, the observer in the car, moves towards the source. So let's say that right here is the source of sound. Okay, here's the observer in the car moving towards the source like so with the speed VO. Here's then how we construct our equation. Okay, first of all, in the denominator of the expression, the speed of the source is equal to 0, the source is stationary. So then therefore we just have v, the speed of sound, in the denominator of the expression. Okay, now in the numerator of the expression, we have the observer moving towards the source. The top symbol means towards, so then therefore we use the plus sign in the numerator. That's the top symbol. Like so. And now we just fill in, and then ultimately we then calculate our Doppler shifted frequency. So in the numerator of the expression, we have here 343 plus 20, so 363, and then divided by the speed of sound, 343, and then multiply by 500 hertz. And we end up then with a Doppler shifted frequency of 529 hertz. So you hear a higher pitched sound. Okay, then in part B of the example, as we'll call it, it says, what happens, that is, if the observer moves away? Well, then picture it like this. So once again, here's the stationary source, but now the observer in the car is moving away like so with the speed VO of 20 meters per second. And now let's go ahead and construct our equation. In the denominator of the expression, once again, we just have the speed of sound V because the source is stationary. And now here, for the numerator of the expression, we have the observer moving away from the source. So if the observer moves away, then we use the bottom symbol in the numerator of the expression, which is the negative sign. Like so. And now we just plug in. So in the numerator, it's 343 minus 20, and then divided by 343, multiplied by 500 hertz, and you end up then with a lower pitched sound. It's about 471 hertz. There we go. Like so. So never mind deriving the expression up on the top board. As I said earlier, that's a little bit beyond the scope of this class, but using the expression is relatively straightforward. Okay, now in the next video that I'll construct here or record, we'll see what happens if both the source and the observer are moving.